with this, and like judging by the amount of people in the audience, I don't really need to tell you much about our next speaker. I think this is like the fullest the room's been. So I'll keep it very short and brief for the introduction. So our next speaker is a co-founder of SpaceX. But what I was also, or even more impressed, is the story how he got there and like the background that he has. So he has worked 15 years in aerospace before that, but he really like was so passionate about it that he started designing like rocket engine in his garage. So, and I asked him like earlier today, saying like, okay, anything happened? And he said like a lot of the experiments kind of blew up, but he didn't injure himself or anybody else. So I'm very glad that he managed to get past that. And I think it's like a great honor to have one of the men who has designed like the engines of some of the most powerful rockets in the world, to have him here in Cluj. So now I need you all to give the best applause that you can for Tom Mueller, co-founder of SpaceX. Thank you so much for joining us here in Cluj. It's a great honor to have you here. Thank you.
Thank you. Yeah, thank you. Yeah, as he said, I'm Tom Mueller. I'm a founding member of SpaceX, and I started out as the vice president of propulsion. So we developed all the rocket engines and propulsion systems for the launch vehicles and the Dragon capsule. Then in the last 6 years, I got changed to the propulsion CTO, and more recently, I'm sort of semi-retired. I'm a senior advisor to SpaceX, kind of helping out where I can. And I just wanted to have a disclaimer here. I'm just here. A friend asked me to come give this talk. It's in no relation to SpaceX. They're not sponsoring me. This is just my own opinion, so take it at that. But anyway, I grew up in a small logging community in Idaho, in the United States. And as a kid, I was really interested in science and space. I think I read every science fiction book in our tiny library in that town. And I was 8 years old when I watched them land on the moon. And so I thought that, you know, by the time I'm this age, we're going to be a spacefaring civilization. And we're getting there, but it's not moving as fast as maybe I'd hoped. But I always said if it's possible and it needs to be done, then eventually the technology will catch up and it'll be done. And I think we're getting very close to where we can use space to save our Earth. So let's talk about that. I think technology has really improved the human condition. It's greatly reduced the number of people living in extreme poverty in the world. In fact, it's recently got below 10%, which is something to celebrate, and it's getting lower. A huge increase in literacy. The life expectancy has more than doubled since ancient times, and by any measure, human productivity per capita has gone up hugely. And in fact, in the US, technology has helped improve emissions. So even though the GDP and population go up, in the last 40 years, really bad emissions like nitrous oxide and particulate and hydrocarbon emissions are way down. And in fact, in the last 10 years, even CO2 emissions have leveled off. So it seems like there's some hope for humanity with technology improving things. But then there's the rest of the world. China and India and the rest of the developing world are growing extremely fast, and their demand for power, unfortunately, means that they're building coal plants, which is the least desirable form of energy from a standpoint of emissions and human safety. And even though by the end of the century, they predict that human population will level off at about 10 or 12 billion people, the energy use per capita is expected to continue to grow. In fact, even though population is growing moderately, GDP is growing extremely rapidly, and resource use, minerals and fossil fuels, and energy production are following more closely to GDP, not surprisingly. And when you grow at a constant rate, that means that you're using resources exponentially. So what does exponential use of resource mean? I got this chart off of Twitter. I thought it was kind of cool. If iron use continues to grow at just 3% per annum, like it has for the last 10 years, within 500 years, we would have to consume the mass of the moon in iron. Well, you're not going to be able to mine that on Earth. So if this resource continues to grow, we're going to run out at some point. And you can see on this chart, like 7 orders of magnitude increase in use of these minerals. And you might say, well, this is hundreds of years, we got time, but look at power consumption for compute. If we stay at the current level of computational efficiency and grow at the current level that compute is growing, which is very rapid, before 2040, it would take the world's power production, current power production, to do compute. But they expect that in those years, there could be a 3 order of magnitude decrease in power, or 1,000 times increase in compute efficiency with quantum computing. But that only delays hitting that power level by 9 years. So this shows that we could be just decades away from running out of some resources. Uh-oh. There we go. So what I'm talking about here is the Earth is finite, while space is really big. Human resource intensity may continue to grow exponentially. The Earth will reach a point where it cannot sustain the quality of life to humans. And at this point, space resource exploitation may be the only way for continued growth. But there are people that say, wait a minute, why should we go and exploit space? We're destroying our environment. Why should we destroy the environment of space? And many would argue that there is really no environment of space. There's no natives to displace. But if we did decide that we were going to stay confined to the Earth and not use the resources available to us, available in space, we would have 2 choices. We would have to slow down and just reach a steady state balance with nature, which sounds like a good plan. Or we just continue to grow like we are until we just reach resource collapse and massive damage to the environment. So I think that it's not within human nature to slow down and reach a balance. I think humans always expand beyond their horizon. 124,000 years ago, Homo sapiens in Central Africa ran out of resources, and they crossed the Sahara Desert into Europe and onto Asia and into the Americas. And then 500 years ago, Europeans discovered the technology to sail the oceans, and again, humanity moved throughout the world. So I think as soon as the technology becomes available, humans use it and expand beyond the horizons. So I think we need to go to space in order to preserve humanity from this massive resource growth. The Earth is the only oasis of life that we know of in the universe, so we should do whatever it takes to protect it. So if we're going to get into space and really commercialize space, what are the barriers? And the first barrier is it's very expensive to get into orbit. And the reason why is rockets are expensive, and rockets were always designed originally as throwaways because rockets were weapons. The very first mass-produced rocket was the V2 used by Germany in World War II. The very first man in space, Yuri Gagarin, went up on a converted Soviet ICBM, the R-7. The first Americans to orbit space went up on US converted ICBMs, the Atlas and the Titan. So these were all designed to be throwaway systems, very expensive. The US tried to do a partially reusable system, the shuttle. We flew it for 30 years, but it never got anywhere close to meeting flight rate or cost. So we kind of gave up on reusable until recently. But current launch vehicles are still pretty expensive. It's like on the order of $100,000 a kilogram for a small launch vehicle. And the lowest cost of access to space is still about $1,000 a kilogram, which is still too expensive to really do what we need to do to save the planet. So I think that fully reusable, rapidly reusable spaceships are going to be needed to get the cost down to below, say, $100 per kilogram, and even lower before you can truly save the planet by using the resources in space. And that's expected to happen in the coming decades. The first use of space is space tourism, the first commercialization. 7 tourists have already flown to the space station on Soviet rockets. And in fact, NASA just announced that they're going to fly from the US to the space station. And a bunch of people have already signed up at over $50 million a seat. Virgin Galactic has signed up hundreds of people at $250,000 a person to fly suborbital. And I think as soon as really low-cost, reusable launch vehicles are available, this could be a huge business. And maybe space tourism is not like a save the planet business, but it's going to help us learn how to live in space and certainly get the economics down to where humans can get to space affordably. The next target is the moon. The moon is sometimes called the 8th continent because it's gravitationally trapped to the Earth, and in fact, it was formed from the Earth by a massive impact about 4.5 billion years ago. So it's a natural target to go to the moon. There's many commercial companies that are targeting the moon with lunar landers. In fact, just a couple months ago, the Israelis tried to land a lander on the moon. They were unsuccessful, but they were the first company to orbit, the first private company to orbit the moon and attempt to land on the moon. And NASA has recently announced the Artemis project to take people back to the moon by 2024, this time to stay. ESA, the European Space Agency, is proposing international moon village. So the moon seems to be really hot right now. And why do these companies want to go to the moon? The first reason to go is water. Water is the oil of space. You can use energy from the sun to convert water into hydrogen and oxygen, which is excellent rocket fuel for moving around in space. It just so happens that these rocket engines run fuel-rich, so there's extra oxygen from the production that can be used by the astronauts to breathe. And of course, the astronauts need the water to live, and the water that you store actually makes a really good radiation block. The poles of the moon have these permanently shadowed craters shown in blue here, and NASA estimates that there's between 100 million tons and 1 billion tons of water at each of the poles. So there's lots of water there to be mined. And for every ton of water that you mine, you can also get many kilograms of sulfur compounds, nitrogen compounds, and carbon compounds. So all the things that you need, the chemicals you'd need to support life there. This is a plot of the illumination of the sun on the poles of the moon. If you set up a base on the peaks of a crater rim near the pole, those peaks are in the sun about greater than 90% of the time. So if you raise solar cells up like 10 meters, you would have almost continuous power on the moon. And only a few kilometers away, down inside those craters, is all that water resource. And there's other good reasons to be on the poles. The temperature, even though it's very cold, it's consistent. It's more consistent. So you can use the solar energy there to keep your habitat at a consistent temperature. Whereas at the equator of the moon, the daytime temperature is hotter than boiling water, and the nighttime temperature is cryogenic, like the temperature of liquid oxygen. So really big extremes of temperature if you're at the equator of the moon, so it makes it very hard to survive there. And you got to remember that a day on the moon is 28 days. It's 2 weeks day and 2 week night. So it's very hard power-wise to make it through the night if you're relying on solar power. In fact, the Chinese landed a rover on the far side of the moon earlier this year, and they shut off for 2 weeks to make it through the night, and then when the sun comes up, they turn it back on. So that's one of the reasons why the poles are favored, at least initially. So it's not just a new space race, it's a new moon race. There's lots of commercial companies that are building landers for the moon. NASA's looking at going back to the moon. China is really big about going to the moon. India. And they're all headed targeting the poles of the moon for the reasons that I just mentioned. But it's not just the poles that are valuable. There's, like I said, the moon was formed from the Earth, so the same minerals that you would find on the Earth you can find on the moon. Iron, aluminum, titanium, and a lot of the companies are looking at the platinum group metals that are on the surface of the moon. The moon doesn't have any tectonic activity, so the surface is very old, billions of years old. So all of the asteroids that have crashed on there over billions of years are still there. So you can mine that for precious metals. There's also an isotope of helium called helium-3 there that makes an excellent fusion fuel. So some people think that could be one of the most valuable resources on the moon if we ever get fusion to work. So let's talk about how much energy it takes to get something from Earth out of the gravity well of Earth compared to the moon. This chart here shows the rocket velocity that it takes to escape the gravity of the moon, and it's about 12.6 kilometers per second to escape Earth's gravity, whereas to escape the moon is only about 2.6 kilometers per second. That's a ratio of just about 5. But energy goes by the square velocity, kinetic energy, and that's more relatable to the amount of propellant it would take to move something off of these bodies. So if you square that velocity ratio, it's more like a factor of 23. So it takes 23 times as much energy to move 1 kilogram off Earth to, say, Mars than it does from the moon. So that's why you'd want to mine the resources on the moon, and then you can move them quite easily anywhere else within the inner solar system. Some people like to look at it more as a potential energy in a gravity well rather than as kinetic energy. So this just shows like the equivalent altitude you have to move something to escape the gravity of the Earth. So it's 6,400 kilometers to escape the Earth's gravity versus 288 kilometers to escape the moon gravity. Again, that ratio is about 22. So it's consistent with the previous calculation. Another huge resource in space is the asteroids. And there are several companies that are targeting mining of the asteroids. One of the most prominent ones is called Planetary Resources. And if you look at their website, they say there are about 16,000 identified near-Earth asteroids that they estimate contain about 2 trillion tons of water. That's trillions with a T. And many of those asteroids are closer delta V-wise, like easier to get to than the moon, like less than 6 kilometers per second from low Earth orbit to get to these asteroids. The asteroids are made of the same things that the Earth is. They contain all the minerals that you could find on Earth, lots of water, as I mentioned, and a lot of the companies' business plans are targeting the platinum group metals because those metals can be brought down to Earth before the infrastructure is in space. So it's an easy way to get a return on investment is to get the platinum group metals. But I think the real save the planet use of these materials would be the structural materials and the water to make propellant. So once you have all these materials in space, then you can start manufacturing in space. And the idea is that you do energy production in space, and you move heavy industry into space using the resources of space. This is the real save the planet mode. This is what really moves the needle on reducing the exploitation of the resources on Earth. And the next step is assembling in space. So you have these assembler robots that form these truss structures, kind of like a spider spinning giant webs. So the first things you might build in space would be gigantic solar arrays to gather up power for the uses of manufacturing in space, or form a large parabolic mirror so you can focus the heat of the sun for manufacturing. Make giant antennas so you can communicate with near Earth asteroids, activity going on there, or beam back down to the Earth. And eventually you would build shipyards in space where you would build spaceships that could go out throughout the inner solar system and get these resources. And you would set up basically gas stations of hydrogen and oxygen all over the inner solar system so these ships could move about and open up these shipping lanes basically in space. Once you get to that point, the next step would be colonizing of space. One of the proposals is what's called an ONeill cylinder, where people can live in a high-quality environment in space. And colonizing space allows it allows us to relieve the Earth's resources, and people still have a very high-quality life in space. These ONeill cylinders are envisioned to be about 20 miles long and like 5 miles in diameter. And they would spin, so they'd have about 1 g of gravity. They'd have a self-contained biosphere inside. They'd be protected from cosmic radiation, have a very controlled environment, have a day-night cycle with mirrors and doors to stay with the diurnal cycle. And it's been estimated that the mass of all of the material in the asteroid belt, if it was converted into space stations like this, you would have as much surface area as 3,000 Earths, 3,000 times the Earth. And that's significant because if you take all of the solid bodies in the solar system right now, it's only about 10 times the surface area of the Earth. And many of these bodies, like, say, Venus, or some of the really cold moons far out there, are not going to be easily habitable by humans. So if you're going to move a lot of people into space, I think the ONeill cylinders would be the right way to go because you can just get so much surface area. But in the meantime, colonizing Mars looks promising. Mars is the one other planet in our solar system that could possibly support human life. It has an atmosphere, although very thin, but at one point in past history it was quite thick and it was very Earth-like, and there was liquid water on the Earth, on Mars, I'm sorry. And it still has a thin atmosphere which helps prevent some radiation from reaching the surface and also blocks micrometeorites from hitting the surface. It happens to have a 24.6-hour day, so almost the same as Earth, so it wouldn't mess up the human biorhythm. Some of the problems that are possible with Mars, it only has 3/8 Earth gravity, and it's not known if humans can live long-term in lower gravity, so that's kind of an unknown. Also, with that thin atmosphere, it doesn't block a lot of the radiation, so you'd have to live under about 2 or 3 meters of regolith to stay away from long-term radiation effects. And the air is too thin to be able to live in it without wearing a pressure suit. So you'd probably want to live in like domed cities like this that are shown here. And power is kind of a problem there too, because it's 1.5 times as far away from the sun as the Earth. So the solar power is weaker at the surface. It only has an 8-hour day. And dust storms can block your solar power for weeks or even months. So nuclear power might be required in order to survive there long term. The next step after you colonize Mars would be to try and terraform it. Now, lots of books and papers, both fiction and nonfiction, have been written about terraforming Mars. And it seems like it might be possible. It's not easy to do planetary engineering. You could get oxygen by photosynthesis of the carbon dioxide that's in the atmosphere. That probably wouldn't be enough. You probably also have to get oxygen from the minerals on the rocks on the planet. You'd need to heat it up to get liquid water. There is lots of water there, but you want to get it warm enough that you have liquid. And some of the ways that have been proposed to heat it are to build giant mirrors in space to focus more solar energy on the planet, or to mine fluorine compounds and make fluorocarbons in order to have a super greenhouse gas effect. Or even some people propose taking comets and bombarding the planet with comets to add atmosphere and heat up the surface. Well, I've done some of these calculations myself, and the amount of atmosphere you'd have to bring to Mars in order to get it, like, say, half of Earth's atmosphere where you could live without a pressure suit is about 200 trillion tons. So it's a lot. The amount of power you would have to generate in order to warm up Mars is about 1,000 times the current world production of power applied over 50 years. So I think we're quite a ways out from having the ability to terraform Mars. I think it's going to take a long time to get to that level of engineering. So in the meantime, we'd probably end up living in dome cities like were shown on that previous chart. So anyway, that's just what I want to talk about today. It's kind of a fool's errand to try and predict the future, but it sure is fun to talk about. But I think what I wanted to show was that I think we're getting pretty close to having the technology available to go out and use space and live in space, and ultimately to protect Earth, the cradle of life. So I think it's a really exciting time to be working with space. Thank you.